Welcome to my classes on fundamentals of electrical engineering. We were doing signals and systems as a part of the fourth module. We have done about 6 sessions in continuous time system, focusing mostly on linear time invariant systems. Now we move on to discrete time signals, and so we may have a little bit of Z transform, mostly Z transform for solution. So we have 3 sessions here. So let me go to the first question. But before we proceed further, let me also try to caution you to the effect that the way that we look at discrete time system is not actually a full continuation of the continuous time system. We may require a different kind of approach, and let me hope that we will be comfortable in discrete time system also, because this is again another wonderful area that gives us a lot of fundamental questions in the gate examination contest. So moving on to the first question, as was mentioned earlier, convolution is very pervasive. Even here, convolution is important and useful too. Okay, it's a tool, by the way. Let Yn denote the convolution Hn and Gn. So when you are convolving two discrete time signals, the procedure happens to be the same. That is, first and foremost, you take them both Hn and Gn to the new axis. In this case, normally it is k axis. From n you move to k. Okay, or from k you move to n. And thereafter you fold one, and then you allow that to push further such that they are overlapping each other, and that each of these sequences that overlap are multiplied and also added, rather than integration, it's summation here, and the result happens to be the convolution. Okay, so here we are given Hn as equal to 1 by 2 raised to, this is a sequence of magnitude starting at n equal to 0, it is half, and then it subsequently continues to reduce, the magnitude continues to reduce. And it's a right-sided signal as signified by un. And Gn is a causal sequence, which means that again this is also right-sided. Okay, if y0 equal to 1 and y1 is equal to half, okay, or in other words, y0 is equal to 1 and y1, that is at n equal to 1, is equal to half, and g1, then what is the value of g1 is what is asked. Okay, so since convolution is already suggested, we take yz, okay, and it's given by, we know one of the sequences and the other is also a causal sequence, so we club them together as two sequences such that the common multiplication factor is k. Then the first sequence Hn is converted to z by z minus 0.5, and so accordingly Gn is also converted into z by z minus a. Okay, so now we have two components. When we take the Laplace in the z inverse, here we have to again compute the two residues. Okay, so a and b happen to be the residue, and a will give you minus 0.5. You get a into 0.5 raised to n. The other component will be, the other residue based on b will be giving you a z inverse of b into alpha raised to n, because we have chosen alpha as the pole for the second, or the sequence value for the second signal. Okay, so now you see that now we can substitute for y0, where y0 is equal to 1, that will be given by a plus b, because n equal to 0 gives you 1 for both 0.5 raised to n as also alpha raised to n. Next comes y1. y1 is equal to half, and we realize that 0.5 raised to 1 is half. Okay, so and that's all. So a equal to 1 and b equal to 0, or b equal to 0 or alpha equal to 0, or the second component g1 is equal to 0. Any of these components can be surmised. Obviously G1 is equal to 0. Okay, so that's how you can solve the first problem. Okay, so let's move to the next one. Here again convolution is given, but in a pictorial sense. Okay, so let's look at this particular problem. Given the finite length input xn Okay, so xn is shown as 1 minus 1. Okay, so it's a very limited sequence having only two components, 1 and minus 1. Okay, and the corresponding finite length output yn. Okay, yn is given by 1 0 0 0 minus 1. Okay, so it has now 1 2 3 4 5 components. Okay, of an LTI system as shown below. The impulse response Hn of the system. So impulse response Hn works on xn and you get yn. So that's one way of looking at it. And others, of course, xz multiplied by hz will give you yz. Okay, and so you can find out what is called as hz. Okay, and then take its Laplace inverse. Third, of course, is going through the convolution process. Okay, so what do you mean by the convolution process? First and foremost, both the signals, there is xn as also hn, are taken to the k axis. So we have xk, which is now folded back. So it becomes x minus k. And so at the head of the sequence of xk happens to be 1 and the tail happens to be minus 1. Okay, and then they move into gk, and then as and when they align with respect to each other, overlap, they multiply, and then the total sum is taken, and that is output as the n value. So we see that since we are having since always so either the tail of xn or the head of xk, sorry, not xn, x minus k will be out of the area of overlap between hn and hk and x minus k. We see that since yn has 5 components, we will have 4 components for hn. Okay, so there are 4 blanks in hn, and we are slowly trying to see what is going to happen. Okay, so at two ends of yn we have 1 and minus 1. So obviously we will have 1 and 1 at two ends of hn, because they need to be multiplied and then the result needs to come out. Okay, so first the new head of x minus k, that is 1, moves into 1, and so we have 1 into 1 as the output of yn. Okay, this is a visual kind of thing that is better better understood at this point of time, because you can imagine and do it very quickly. Okay, so one important point is how many components will be there in hn. It will have you'll have to remember that the head and the tail, either of them, okay, will be out. So you'll need 4, so instead 4 and 2, 4 and 1 5 will prepare you for 5 outputs in yn. Okay, so we'll see. So the two ends have 1 each, such that when the tail of x minus k matches with hn, we are going to have an output equal to minus 1. Okay, so in between, what is going to happen is that you have both 1 and minus 1 coming together. Okay, so it will be 1 on one of those, and the other will be on minus 1. So you need to have so there needs to be a cancellation. So we'll have 1 1 both as the two internal signals of hn. So we have 1 1 1 1 as gk coming out, such that we can see that, okay, sorry, as hk coming out, such that we can have we can diagnose hn as equal to 1 1 1 1, and so C option is correct. Okay, so let me hope to repeat this particular problem. Here we have a situation wherein we have the convolution process being explained using 2 signals. Okay, so one is xn and the other is hn. The first process is to take them to the new axis, which is k. In this case, it is k. If it was if the two values were given as xk and hk, you could have easily moved on to xn and hn. Okay, so one of them needs to be folded. In this case, because xn happens to be more limited when compared to hn, we fold xk to minus xk. Okay, so now why do we say that hk is a little lengthier than xn? The sequence hn is lengthier than xn. Why? Because you have to look at the output, and the output has 5 different components. In the sequence yn, we have 5 different components. If that is so, then either the head or the tail of xn is outside. So you just get, there are only 2 components. So you need to add, you need to have 4 at least in hn, such that you have 5 components in yn. Okay, so this is the way that you look at it. Okay, so either the tail or the, okay, so if it was a longer one, you would have more. Okay, so we might encounter such problems again. So now, if this is the case, you start the xk, which has been folded and is now x minus k, is now moving into hk. So what we have there, we see that at either ends we are having a repeat of whatever is in xn. It's in x minus k. So how can that happen? Only if hk has 1 at 2 of its ends. So only the internal components are now going to matter. What about the internal components? The internal components, we realize that we are going to have 1 and minus 1 slowly overlapping each of the 2 components. So if you multiply 1 by 1 and the other by minus 1, then together they cancel, and so the internal components of yn, that is when you compare the other 2 ends, all the 3 components will be equal to 0. So that's the reason why, since there are 4 components, you can see that we have this has to come to the very end. That's the reason why we see that we are having n as equal to 1, 1, 1, 1. Okay, so as simple as that. I suppose it is well understood. And through this you internalize a few things, such that when problems of these kinds come, you don't need the diagram that has been drawn here to explain the property problem. So let's move to the third problem. This here again, the z times of a signal xn is given by 4z raised to minus 3. So this is okay. Z raised to minus 3 tells us of a delayed signal. 3 into z raised to minus 1. Again, the signal is delayed by 1 time unit. Okay, 2 means the signal happens to be at n equal to 0. Minus 6z square talks about a signal which is non-causal, a signal component which is non-causal, which is advanced by 2 time units. And 2z cube is also a component which is advanced by 3 time units. If it is applied to a system with the transfer function hz is equal to 3z raised to minus 1 minus 2. Okay, of course, this is a purely causal signal, hz, 3z raised to minus 1 minus 2. Let the output be yn, which of the following is true. Okay, so of course, we know that when you are having 2 signals, xn and the input signal being given to a system as shown by hz, then yz or the z transform of yn will give you yz, which is equal to xz hz. Okay, so we have to multiply them. Okay, so you can multiply them. Meanwhile, let's see what is asked out of us. Let the output be yn, which of the following is true. So we'll read the results and then we'll go back. Yn is non-causal with finite support. Okay, so with yn is non-causal. No, yn is yn is non-causal. Why is it non-causal? Because 2 into z cube multiplied by z raised to 3 into z raised to minus 1 will still give you 6 into z raised to 2. Okay, similarly, minus 6z square multiplied by 3z raised to minus 1. These are the largest powers in z. In xz, if you multiply it by 3z raised to minus, still it will give you a non-causal signal. So option 1 is true, and there we can stop. Okay, but there's something added to it. Is non-causal with finite support. The signals exist only for a short period. Okay, so for a limited period. That's why it's called as for a finite time period. So it's called as a finite support. Okay, so let's move to the next one. A signal is processed by a causal filter with transfer function gs. For a distortion-free output signal waveform, gs must be. So here we are back to Laplace transform. But if we are processing a causal, if a signal is processed by a causal filter with transfer function gs for a distortion-free. Okay, so if you want to have a distortion-free output, then you can only go for what is called as a linear shift. Okay, so phase shift has to be linear. Otherwise, you will have what is called as. So we will see in the next subsequent one why is it so. Okay, provide zero phase shift for all frequencies. No. Provide constant phase shift for all frequencies. No. Provide linear phase shift that is proportional to frequency. Okay. Provide a phase shift that is inversely proportional. That's also not true. Okay. So let's look at the next problem which might make this particular question clearer. Okay, a signal is processed by a causal filter with transfer function GS. For a distortion-free output signal waveform, GS must be, okay. So GS is given as GZ. Okay, of course that's why this question is put in this session. Okay, so GZ is equal to AZ raised to minus 1. So what is happening is, this is the shift that is happening. Okay, so multiplication by A and a shift by, or Z raised to minus 1 is also called as a delay unit, as you very well know. Okay, plus beta into Z raised to minus 3. So there is a shift by one time unit, as also by a time unit by of 3. Okay, it is a low pass filter, digital filter. The phase characteristic same as that of the above question. So now it should not have any distortion. So how can that happen? Only if alpha and beta happen to be equal. Otherwise, what is going to happen is that when it gets shifted, then the multiplication factor changes, and so there's going to be a distortion. Okay, so we have the first option is obviously true. Alpha should be equal to beta. Okay, so this answer and C in the previous question matches, wherein the phase shift is linear, such that you are having what is called as a no distortion system output. No, not an output which is not distorted as a result of only linear shift be happening on it. So let's move to the sixth question, where we are given a picture of a forward transfer function GZ, and there is a feedback of amplitude K, and it's a positive feedback. So be careful about it. It's a positive feedback. It's not a negative feedback, which normally assures more stability. Okay, so consider a discrete time system shown in the figure, where the impulse response of GZ is. Okay, so the response of GZ is given as equal to GZ is explained as equal to G0 equal to 0. So if you set up a time sequence, you can see that at n equal to 0, G0 is equal to 0. Okay, at n equal to 1, or G1 is equal to G2 is equal to 1. So you are having two values. Okay, delayed of course by Z raised to minus 1, delayed as given by Z raised to minus 1 into 1 and Z raised to minus 2 into 1. Okay, because the amplitude is equal to 1. G3, G4 and the rest are all equal to 0. So it's again a limited sequence, wherein you're having an amplitude equal to 1 only at n equal to 1 and n equal to 2. Okay, so how do you explain this signal? It's very simple. It's the same as equal to Z raised to minus 1 plus Z raised to minus 2. Okay, so how do you get the overall transfer function? GZ divided by 1 plus GZ HZ. In this case, it is 1 minus GZ HZ. So we have Z raised to minus 1 plus Z raised to minus 2 divided by 1 minus K into Z raised to minus 1, Z raised to minus 2. So the result is, of course, multiplying throughout by Z square. We see that on the numerator you have Z plus 1, and on the denominator you have Z square minus K into Z square moves inward, so we have Z plus 1. Okay, so that's so far so good. And what is the question? The system is stable for the range of value of K. So how do you ensure stability? For discrete time systems, the stability is ensured by having the poles of the transfer function as the overall transfer function inside the unit circle. So how can you have it inside the unit circle? For one thing, of course, we can see that you can have a value of K as equal to the largest limiting value of K as equal to minus 1, one of the limiting values, such that we have Z square plus Z plus 1, such that the two roots are now, the complex roots are minus half plus root 3 by 2j and minus half minus root 3 by 2j. So that's acceptable. It's of course the limiting case because they happen to lie on the unit circle themselves. Okay, so now what about the other? So of course the other is where we are having Z square, that is the other pole, that is Z given by Z square minus KZ plus 1 minus K as equal to 0. Okay, you set it as equal to 1. Okay, such that such that you are limiting it inside the unit circle. Okay, so now to find the you are finding the poles from Z square minus KZ minus K by finding out the by setting it as equal to 0. So we have a K plus or minus square root of K square plus 4K by 2 as equal to 1. Okay, so you solve it, or you say that 2 minus K whole square is the same as equal to K square plus 4K. So K square and K square cancel. So you are having 8K is equal to 2, or K as equal to 8 square is equal to yeah, you have, yeah, so you can see that k is equal to, so just solve it out, you can see that k is equal to half. Okay, so there are two limits for k. One is -1, wherein we see that we are having the only case wherein the poles happen to be of course complex, but they happen to be on the unit circle. The other happens to be when when we are setting when we are finding the poles based on z square plus kz minus kz minus k is equal to 0. Okay, so or finding the poles. Okay, and you set it as equal to 1. Okay, so you see that you can solve it, and you can see that k is equal to half. Okay, so as simple as that. I suppose it's clear. So here we are, both the cases have been explained to you based on the fact that we want the poles to be at the most on the unit circle. Okay, so at the most. Okay, so let's move to the seventh problem. X is equal to 1 minus 3z raised to minus 1. So we have or in other words, xn happens to have a value equal to 1. Okay, happens to have xn is equal to 1, or there is a impulse at n equal to 0 such that you can convert it into its set transform as equal to 1. There is also another impulse which has a magnitude equal to 3, and it is delayed by 1 time unit, or delta n minus 1. Okay, or minus 3 into delta n minus 1. So this is all. Okay, let's see what is yz. Yz is equal to 1 plus 2 z raised to minus 2, which can be similarly understood if required. Okay, so only if it is required. So if it's not required, let's not go for that. Okay, our z transforms are two signals, xn and yn. Okay, we try to think in terms of what is xn. Okay, so yn can also be similarly diagnosed if required. A linear time invariant system has the impulse response hn defined by these two signals as hn is equal to xn minus 1 convolution yn. So we have we know what is xn, of course, or you can find out or you have what is called as xn from z inverse of xn, and so you can also get what is called as the z transform of xn minus 1. Why do we need the z transform xn minus 1? Because convolution tells us that you can take the z transforms of both yn and xn minus 1, and you can multiply them, and you can, if required, you can take the z inverse and obtain hn. Okay, so where star denotes the discrete time convolution, then the output of the system for the input delta n minus 1. So we have the impulse response. Now we need to have what is called as the output as given by, let's say, yn. Okay, and we also see that we have the input as given by delta n minus 1. So what is hz? First and foremost, what is the output in the z transform domain? First and foremost, we have what is called as the xn delayed by 1 time unit, or z raised to minus 1 multiplying 1 minus 3z raised to minus 1. So we have z raised to minus 1 minus 3z raised to minus 2. Okay, multiplying. So that gives you xz. Now we can find out that gives you xz, and now we can convolve it with yz such that we can get hz. Okay, and then you have to again multiply hz by the z transform of delta n minus 1. Okay, so the z transform of delta n minus 1 is z raised to, okay, so of course it's located at n equal to 1, so z raised to minus 1, and this z transform is 1, so z raised to minus 1 into xz, which is equal to z raised to minus into x of x, the z transform of x n minus 1, which is z raised to minus 1 minus 3z raised to minus 2 multiplied by yz, that is 1 plus 2z raised to minus 2. So everything can be multiplied together. The result is z raised to minus 2 plus 2z raised to minus 4 minus 3z raised to minus 3 minus 6z raised to minus 5. And what is asked out of us is that then the output of the system for the, okay. So now we just need to take the z inverse of this. So we can start off from the first component, wherein we see that, okay, we see that we have a delayed impulse as the z inverse of z raised to minus 2 by 2 time units. So delta n minus 2. The next component is plus 2 times the amplitude is there, again delay by 4 time units, so delta n minus 4. Okay, so then we have delta n minus 4, and then we have minus 3 Okay, so minus 3 is there, and it's a delay of 3 time units, so delta n minus 3, and then minus 6 delta n minus 5. Okay, so only one that is option. As it is, you move towards option B when you see a setup like this, and then as and when you just check out whether you are arriving at the correct answers, and once you are right, once you're sure that you have the correct answer, you stop there. Okay, so option B is correct. Okay, you don't need to look at other things. Okay, and of course, let's just examine A. A tells us that Z transform of Z raised to minus 1 x z y z. No, we have to find out what is called as the Z transform of xn minus 1 and not xz. Okay, and the C option is Z transform of 1 minus 3 Z raised to 1. Okay, it's not, that's not true. Okay, does not satisfy any of the above three. That's also not right. Okay, so moving to the 8th problem. Again, what is given is x n equal to 0. Okay, and x n equal to 0 where n is between minus 1. Okay, n is less than minus 1. Okay, at n equal to okay, so we have what is, yeah, so we at n equal to n greater than 0, x minus 1. And okay, so this is true for n is less than minus 1 and n greater than 0. Okay, so but x minus 1 is given as equal to minus 1. Okay, and x0 is given as equal to 2. So there are, again, it's a two component sequence wherein we are having x0 is equal to 2, and we also have x minus 1 is equal to minus 1. The other values are 0. Okay, and so we can find out xz as equal to, yeah, so we have minus 1 located at x minus 1. There is amplitude minus 1 located at n equal to minus 1, or in other words, it's minus 1 into z. Okay, not z raised to minus 1, but z. Okay, and then you also have x0 with an amplitude equal to 2. Okay, so you can take its z transform as given by 2. Okay, simply 2. Okay, yeah, so we have 2 minus z as the yeah, it's an impulse of amplitude equal to 2. So we have 2 minus z as z xz. Okay, and so yeah, let's move to the next component. Yn is equal to 0 for, again, n is less than minus 1. Okay, so that, and n is greater than 2. Okay, but we have y minus 1. With an amplitude is equal to minus 1. Immediately you can convert it as equal to minus 1 into z. Okay, and then y1 equal to, yeah, this is also equal to y1. So that's z raised to minus 1. Okay, amplitude is minus 1. So minus 1 into z raised to minus 1. And it's all, and y0 is given as equal to 3. So we have to be careful there. Y0 is equal to 3, which means that 3 is without any z. Okay, and then we also see that yeah, so we have yeah, y2 is given as equal to minus 2. What is y2? Y2 is, again, it's a delayed version, so z raised to minus 2. Okay, into minus 2. Minus 2 happens to be the amplitude. Okay, so yz is now easily, if you put them all together, it's equal to minus z. Okay, plus 3 minus z raised to minus 1 minus 2 z raised to minus 2. Okay, is the output of a discrete time linear time invariant system. The system impulse response Hn will be what? Okay, so Hn will be given by, as we very well know, we have yz by xz gives you hz. Okay, so what is yz? The whole so we have minus z plus 3 minus z raised to minus 1 minus 2 z raised to minus 2 divided by xz, which we calculate as equal to 2 minus z. Okay, so now we can, it is easily divisible. And how do you divide it? Okay, so in the descending, because it's a causal system, it has to be divided such that you have the descending powers of z. Okay, so we have yeah, so we see that it's the same as equal to 1 minus z raised to minus 1 minus, only then you will get such a signal because it's cos. Okay, so 1 minus z raised to minus 1 minus, okay, long division method. Okay, minus z raised to minus 2. Okay, so that tells us that h0, okay, is equal to 1, which does not have any z, and then there's a delayed version that happens at 1 time unit 1, or h1 is equal to minus 1 and h2 is equal to yeah, again minus 1. So any answer with that is going to be our solution for the problem wherein we are trying to find out the impulse response Hn. Okay, so we see that now we have A as right. Okay, Hn is equal to 0 0 when between Hn is not equal to 0 between 0 and 2, but of course we see that H0 is equal to, so H0 is equal to 1, H1 is equal to, H2 is equal to -1. Okay, so I repeat, in this case what we did was that we remembered that Hz will be obtained by Yz by Xz. So we calculate Yz and we compute Yz and Xz based on the time, the amplitude, as also the time location of the sequences described by Xn and Yn. Okay, so once you do that, now you must remember that you have to divide the numerator by the denominator, and the order needs to be appropriate such that a causal signal comes out of it. Okay, because it's a linear time invariant system. Okay, so it has to be causal. Okay, so we see that it's the same as equal to 1 minus z raised to -1 minus z raised to -2. So the amplitudes are important, and also the time at which they occur. So at n equal to 0 we have 1, at n equal to 1 we have -1, at n equal to 2 we have again -1. Okay, so try to filter out the amplitude and the magnitude accordingly, and so you will be arriving at the answer very easily. So a lot of compartmentalization is required in this case, and that's exactly what I said when I said that the approach is a little different when compared to the continuous time system signals, okay, or continuous time systems. Okay, so let's move to the ninth problem. This seems to be very easy. If xn is equal to 1 by 3 raised to n, okay, of course absolute value, which means that there are two components to 1 by 3, the sequence 1 by 3 raised to n. One is of course when n is equal to positive, and others when n is equal to negative. When n is equal to positive, we see that it's the same as equal to 1 by 3 raised to n. But on the other hand, when n is equal to negative, we see that it's the same as equal to, of course you're taking the absolute value, but then it becomes 3. 1 by 3 becomes 1 by 3 raised to minus something, so it becomes 3. Okay, so this is what needs to be remembered in this problem. That's all that's required. Okay, and there's another component for the signal, minus half raised to n un. Then the region of convergence of this z transform in the z plane will be what? Okay, so in this case we realize that sequence 1 by 3, as was mentioned, sequence has the first sequence with an amplitude equal to 1 by 3 has two components. For positive, the right sided signal, that is for the right sided signal, z is greater than 1 by 3 is important, and on the other hand, for the negative end, we'll see that the sequence is such that we are going to have the that is below 3. Okay, so less than 3 is going to be the region of convergence. Okay, and of course half is the right sided signal, un is very easily decipherable as having a region of convergence greater than half. So greater than half and less than 3 is going to be the common area for region of convergence, and so we have from amongst the answers option C, where less than 3 and larger than half is going to be the location of Z or the region of convergence. Okay, so this is what we have done today. We have tried to talk about the region of convergence in this manner, wherein the absolute value of n is telling us that there are two components for the signal. One is the right sided signal and other is the left sided signal, and for the left sided signal we see that we are having we are having a region of convergence less than 3. Okay, not 1 by 3 but less than 3. Okay, because of the negative exponent. Okay, for the right side signal, the right side signal is okay because it is going to be beyond 1 by 3. But of course, that's only but we have what is called as two region of convergences overlapping each other, and that is given by the other part of the signal, which is half raised to n. Okay, so here it's a right side signal, so it's the region of convergence is beyond, okay, or around, or is going to be exclusive of the inner region. Okay, so we are having a region of convergence greater than 1 by 2. So greater than 1 by 2 Okay, though 1 by 3 is smaller than that, we can't include it because there's no overlapping. Okay, so we also have less than 1 by 3 coming together as shown in the figure, and so you can easily find out that region of convergence is of Z is less than 3, but at the same time it is larger than half. Okay, so option C. Okay, so that's one thing. Second is, of course, how to find out HN, and then again we also looked at convolution. After convolution and thereafter multiplication by the input, all in Z transform domain. We also had a look at a situation where we are having a positive feedback, okay, and finding out the value of K such that all whatever be the roots of the or the poles of the roots of the characteristic equation or poles of the system inside or on the unit circle. Okay, so we also talked about the phase shift without distortion, and we again talked about how we'll have causal systems only if Z has a negative exponent, wherein that tells us about signals delayed and not signals advanced. Okay. Yeah, we also talked about a convolution wherein we saw that we saw the process. We also found out what is the value of Hn such that Xn convolving with Hn gives you Yn. Okay. So and we started off with the convolution again, wherein we had we had two signals convolving, and and the results were given, from which we saw that G1 is equal to 0. Okay, so this is this rounds of today's session. We'll move on to another session on again discrete time systems and Z transforms in the next session. Thank you.